Okay, next is measures the variation. Measures the variation is about how spread out the data values are, the dispersion of data values. And there are four measures. So range is the maximum minus the minimum, okay, the width of the data, if you will. Then variance, okay, that's a measure that you take the difference between each x value and the x bar value, then square that, and you find the average of those squares. The standard deviation is simply a square root of variance. And coefficient of variation is to express the standard deviation as in terms of the mean. So that way, coefficient of variation is an unit-free measure, if you will. So it can be expressed as a percentage. It's easy to compare two different data with different magnitudes to see which one has larger variation, larger dispersion. So dispersion as a percentage, if you will. Okay, let's come back to the Excel file, the same serial data. Okay, so now we want to compute the standard deviation, and let's do this for calories. Okay, let's set up the data. Yeah. I'm going to just copy the names here. Okay. Okay, so now we have the calories from here. Okay. And we want the average first. Okay, once we have the average, then we can do x minus x bar. So you take x minus x bar, and x bar must be absolute referenced. So this gives us how far is the deviation of each x from x bar. Okay. Now we need to square these deviations so that the negatives and the positives don't cancel each other out. So square that. Okay. Now you sum those squared values, and if you sum this, you'll always get 0, because the x bar is an average of x's. So in total, all the x's combined the deviations will be positives, the negative deviations cancel each other out, and you will have 0. Okay, so now x minus x bar squared. So here is the formula, x minus x bar squared. So we have summed all of those. And then we also need the sample size, so we use count for that. Okay, so now we are ready to compute the variance. Variance is that divided by n minus 1. Okay, and this is called degrees of freedom, because in a sample, if you know n minus 1 values and x bar, we can figure out what the nth value is, because these two are interrelated. So you lose in a sample, you lose a degree of freedom when we compute x bar. So n minus 1 is the degrees of freedom. We divide the sum of squared values by n minus 1, and that will give us the variance. And you take a square root of that, and that's our standard deviation. Okay, standard deviation. Now let's calculate the variance and standard deviation using Excel functions. So now let's do this for all three columns of data on the serial data file. So we're going to do range, variance, standard deviation, and coefficient of variation, all of them. Okay. So for range, we need the minimum and the maximum. So we have min, like that. And then we have max, like that. Okay. So then range is the maximum minus the minimum, the width of the data. Now variance is, we have VAR. Okay. Now you see there are a lot of options under variance. So this is very important for you to understand what the different options are. So you see there are the last two of them with a warning sign. These two are legacy functions. These were the functions that were available, I believe, Excel 2007 and backwards. So these are given only for backward compatibility, and you should not use these two. If you use these two functions, I will be deducting points from your homework and exam and so on. Okay. Now these are the two that are important, and these two do not worry about. So here VAR for variance, dot P is variance for a population, and dot S is variance for a sample. The difference between the sample variance, the population variance, is the denominator is n minus 1 for sample, the denominator is n for population. So if the data that you have represents the entire population, then the denominator must be n, and you should use VAR dot P. But here what we have is a sample of 7 serials, so we need to use VAR dot S and those values, and you see that that's exactly same as what we calculated here using the formula, that formula. Okay. Now standard deviation, of course, we can take a square root of that, or Excel offers STDEV, and again you see there is legacy functions. For backward compatibility, don't use these. Okay, and you need to use one of these two, and mostly it will be STDEV.S, because most of the time we'll be dealing with sample. Very rarely we will be using the entire population data. So STDEV.S, okay, and once again it's the same like what we had before. So now if you copy these across to the other two columns, and you have the corresponding data, corresponding information for the rest of them. Okay. Now for these 7 serials, okay, if you look at the standard deviation, you see the standard deviation for calories is really high and somewhat moderate here and low here. So does that mean that the calories, the variation in calories among the 7 serials is really high? The spread, the dispersion of data is really high? Well, no, because the values here are affected by the magnitude. So the calories are large values, whereas sugar is small values. So naturally your standard deviation is going to be in the same units as calories or same units as sugar. So it's going to be a small number for sugar and a large number for calories, and doesn't really mean the calories are more dispersed than the sugar. And for that we have to convert these variations as a percentage of the mean. So you take the standard deviation and you divide by x bar, that one. Okay. And we can express that as a percentage and copy. And you see here that sugar has lot more inherent variability, 57.8%, even though the number is really small, but the raw numbers are small, and yet it has a standard deviation of 3.39 that represents 57.8% of the mean. So this sugar has lot more variability, and this is especially useful when you look at stock prices. Well, the stock prices vary so much. There are stocks which are priced in dollar amounts. There are prices which are in $100 and $200. So which one has more variability? Okay, and variability being a measure of risk. Okay, so don't compare standard deviation, compare coefficient of variation to see which stock is more risky and which stock is less risky. One more number that we can compute with respect to the dispersion of data is to take the deviation of a given x value from x bar and convert that into number of standard deviations. The z-score represents the number of standard deviations in a given x value is from the mean. So some z values will be positive, some will be negative, okay, but these z values are unitless measures, so it can be compared how many standard deviations each value is from the mean. So let's look at this in Excel. And once again, normally speaking, in most instances, all data values will fall within plus or minus 3 standard deviations. In other words, the z-score of -3 to +3. So if you see a data that has a z-score outside of this plus or minus 3, like 3.5 or 5 or 6 or minus 3.4, -4, then that is a flag that raises a flag that this is an unusual value. This is not the normal case. Okay, now let's compute the z-score for calories. Okay, again, let's set up the data. Okay. So these are the x values. Okay. So now we'll take each x value and subtract the x bar value. So now we are looking at only calories. We are not looking at carbohydrates or sugar. So that minus x bar, so x bar is right there. Okay, x minus x bar. Now we divide that by standard deviation of calories. Okay, so that gives us the z-score. So 80 is 1.06 standard deviations below the mean. The negative sign says that it is below the mean. Okay, I'll copy that. Well, the error here is because the mean and standard deviations must always come from those cells, and I forgot to make that into absolute references. And this is a good way of showing what this error really means. So I have to convert that into absolute references, then those error values will go away. Okay, so you see here the calories for Kellogg Rice Krispies is 130, and since the average is 130, z-score is 0. And here 200 here is about 1.5 standard deviations above the mean. Now all of them are within plus or minus 2. Never mind plus or minus 3. It's even less than plus or minus 2. So we can safely say that all of the data are within the realm of normal values. There are no outliers.